Okay, so I've got the 1.1 PowerPoint up, so I figure we'll go through that. 1.3, where we're looking at linear functions and models. Why don't we go ahead and just recap? So let me just add a page here, or maybe a section. I don't know what we'll call this. I'll figure out something at some point because I already have a 1.3. Those are the notes I used before. But let's just kind of review some of the basics. So linear functions. So the main thing that pretty much we use more than anything, I would say, is slope-intercept form. So this is just your y equals mx plus b. If you want to be particular and you use function notation, you could, instead of using y, say f of x is mx plus b. M is the slope. How is the slope computed? It's change in y over change in x. Or a lot of times you'll have that formula, y2 minus y1 over x2 minus x1. B, or 0 comma b, is your y-intercept. There's a few things to kind of figure out when it comes to interpretation. Slope is going to represent your constant rate of change, and it's going to have units of y over units per x. So it's going to be a ratio of units, like miles per hour, that's distance over time. Or, it could be like people per year. You could look at how the population of a country is changing. So usually there's going to be a ratio of units involved with slope. The y-intercept is typically going to represent the initial amount of some quantity. You could look at, it could be initial temperature of something that is, going to be getting heated up, or it could be the amount of money you would start with a bank account, some initial amount. And that's just going to be whatever the units of the output y are. And again, probably this is review, but that's okay. So when we get into looking at slope-intercept form, two things we want to be able to do very quickly. We want to be able to go from a graph to the formula and vice versa. So let's say I give you a linear function. Can you quickly graph it? So let's start with that example. Let's say sketch a graph. Of y equals 3/2 x minus 4. Okay, so the fast way to do this is always locate your y-intercept. Start there, so I'll make some graph. So my y-intercept is at -4. So I found my y-intercept. And then the slope gives you a set of instructions on moving from one point on the graph to another point. So, right, your 3/2 is your change in y over change in x. So that means if you move up 3 and right 2 from a point that's on our graph, the y-intercept, we should find another point on our graph. So let's go ahead and do that. So if we move from this dot up 3 and right 2, that also must be on our graph. And that gives us a really quick way to sketch a graph. If you have something more complicated that you want to graph and you need some accuracy, because right, graphing by hand is often inaccurate. What's a good website to graph something? So what's a good website to graph something? I like Desmos, so DESMOS.com. It's got a really nice graphing calculator. So if you don't have a fancy graphing calculator, you can just go to this website. So we could type in what we just had, y equals 3/2 x minus 4. And we get exactly the graph we saw. And it's much, much prettier. So you might want to keep that website in mind moving forward. If you ever need to graph anything fancier, there's lots of cool things you can graph. All right, so that is graphing from the formula. Let's go back to and obviously one thing that's going to happen when you graph something with a positive slope, it's moving up as we go from left to right. If you had a negative slope, it would be going downward. So I don't know. Yeah, maybe we'll call this part A. Let's do a part B where we graph something with a negative slope. Let's say sketch a graph of y equals minus 3x plus 7. So again, we find our y-intercept to start. So all the way up here, it's 7. So here we are. And then negative 3, we actually want to think about as negative 3 over 1. So in my mind, this is going to be down 3 and right 1. So from this point, I'm going to move down 3 units, 1, 2, 3, and to the right 1. And I get this graph. So pretty basic stuff there. Okay, so what if I give you 2 points? Can you then tell me the formula? That's the other big thing that you do, right? We said, here's the formula, can you show us the graph? Now, if we have some information about the graph, namely 2 points, can you give us the formula? So this is the other way. And I'll show you 2 methods of doing it. So example, find the equation of the line that passes through I don't know. I'm just going to make up some numbers, 2, 3, and let's say 6, 13. Okay, so for either method I'm going to show you, you always have to start by finding the slope. So let's find the slope. So your slope is given by 13 minus 3, y2 minus y1 divided by 6 minus 2. So we end up with 10 over 4, which is 2.5. So that's our slope. So now from here, there are 2 methods. So method 1, I'll say is the point slope formula. What is the point slope formula? Well, it is, let's say y minus, let's say y0 equals m times x minus x0, where x0 comma y0 is any point on your line. So I know 2 points on my line, 2, 3, and 6, 13, so I can use either one of those. And then I just found my slope m. So basically, you just have this formula memorized and plug everything into it. So I'm going to use 2, 3. So I'm going to have y minus 3 equals my 2.5 slope times the quantity x minus 2. And then usually they'll want your answers in function form or in slope-intercept form, which basically means expand the right-hand side and then add 3. So we're just kind of solving for y. So y minus 3 is 2.5 x minus 5, distributing the 2.5. And then we'll add 3 to both sides. So I get my slope-intercept form as y equals 2.5x minus 2. So that's method 1, using point slope formula. Method 2 is just using the slope-intercept and essentially plugging in. So method 2, I would say plug in and solve for b. doesn't rely on using another formula other than y equals mx plus b. So we know our line has to look like y equals 2.5x plus b. Then basically what you do is you just plug in your point, or one of the 2 points, and solve for b. So I know 2, 3 is on the line. So 2 replaces x, 3 replaces y, and then I solve. So I get 3 equals 2.5 times 2 plus b. So I have 3 equals 5 plus b. I subtract 5 on both sides. So -2 is the value of b, which means my line has to be y equals 2.5x minus 2. So 2 ways to do the same thing. You can do whichever you prefer. They essentially will come out the same either time. I don't know, when I was in high school or whenever I learned this stuff, I think point slope form was more common, but now I think it's the other way. I think method 2 is more common. Anyone does anyone I don't know, I think there's some sort of like polling application here. Yeah, I don't have the desktop app. I'm just doing this through the browser, but I don't know. Is method 1 or method 2 more popular amongst students? Just let me know in chat. Method 2. Like I said, I think that's what I've been hearing as well. Yeah. One thing about point slope formula, I'm telling you, like, oh, it's another formula to memorize. If you think about it, it's really not even an additional formula, because if you take, here's a remark. Point slope is really just the slope formula in disguise. Not a lot of people make that connection for whatever reason, right? What is your slope formula? It's m equals y2 minus y1 over x2 minus x1. Well, what happens if you cross multiply that formula? We get m times x2 minus x1 equals y2 minus y1. Then that's all you have to do is essentially relabel. And if you relabel, make x2, y2, x and y, and make x1 and y1, x0 and y0, you get exactly point slope formula. So really the point slope formula is the exact same thing as the slope formula, just cross multiplied and relabeled. So that might be an interesting fact. All right, so let's go ahead and look through this PowerPoint, see if it has anything useful to offer. Again, you can find all the PowerPoints under the Files section of the Canvas course. Okay, linear models and rates of change. So whenever they say linear model, you can just think linear function, same difference. A lot of times models just have specific applications in mind. So you're going to have some units, you might have some data, stuff like that. This section actually goes into, if you read the whole section, it goes into regression as well. You'll do regression in a statistics course. We don't really use it much in the applied calculus sequence. It doesn't come up very often, so we're going to skim over that. But if you do have questions, we can go over it. A lot of different ways to do regression. You know, usually you're using some numerical tool. Excel can do it. And stat, it depends on what stat calculator they're using in that class. You can also do it by hand, really. All right, so linear models and rates of change. One of the things that is the defining feature of linear models is the rates of change are constant. They never change. And that rate of change is the slope. So Yeah, that is the rate of change. So review of lines, we've kind of already gone over this. This is the pictorial definition of your slope. So rise over run, which also is change in y over change in x. That's constant no matter which 2 points you pick. If you would pick those 2 points, notice they form a triangle. And any triangle you would pick, no matter which points you chose, would be similar to the triangle that's shown. And we know that if you take ratios of sides of similar triangles, you'll get the same proportion. So that's why that works, really, because of similar triangles. And essentially, it's a measure of steepness. So, okay, so there's the slope formula, which we already covered. Y2 minus y1 over x2 minus x1. The delta of the triangle, when I say delta y over delta x, that's the uppercase capital delta in the Greek alphabet. That's used for change in science and math quite a bit. So whenever you see a delta, just think change. Okay, and then we get to the point slope form that we just used. Again, you don't necessarily ever need to use point slope form, but you can if you find it easier. Okay, so there's the point slope form. Same formula we've looked at. Yep, B is the y-intercept. We also noted that. Notice if you plug in 0 for x, that's what you end up with. You end up y equals b because the mx term would vanish. So, and again, we looked at graphing lines. That's the fastest way. Start with y-intercept and then find a second point using the slope. Slope-intercept form, that's the most common and most useful, y equals mx plus b, because you've got y solved for, which is what you want to do when you're writing things in function notation, right? That's why it would be the dependent variable. Y depends on what you would plug in for x. So a lot of times you'll hear independent and dependent variables, and x would be your independent variable and y is your dependent variable because the formula is written in terms of x and y is explicitly solved for. Okay, so here's an example. They find the equation through 2 points. Again, you always start by finding the slope. So -4 minus 2 gives you a -6 on top, and 3 minus -1 gives you a +4 on the bottom. That reduces to -3 over 2. And they are using method number 1. Notice they're plugging in the 2 points into the point slope form. So there you have it. That's the equation of the line there. Again, they rewrote it in terms of slope-intercept, solving for y. Okay. Yeah. This is one good thing to note. So there's essentially four possible graphs. You can kind of group all graphs of lines into 4 categories. Graphs and let's say the relationship to slope. So on the one hand, we already talked about essentially increasing and decreasing being related to if the slope is positive or negative. So if the slope moves upward as you go to the right, you're going to have a positive slope. If it moves downward as you go to the right, that would be a negative slope. So m less than 0. But there's 2 other lines that come up occasionally. You could have a horizontal or a vertical line. So a horizontal line has a slope of 0. Notice all the points have the same y-coordinate on that line. So if you plug them into the slope formula, you would get 0 on top of your fraction. So an example of an equation of a horizontal line would just be like y equals a number, something like y equals 5. That would be an example of an equation of a horizontal line. A vertical line is actually not a function, so it doesn't pass the vertical line test, right? But we can still talk about it as an equation. Let's say we have this line right here. If you tried to plug in some points, all of them here have the same x-coordinate, which means if you do the slope formula, you're going to end up with 0 on the bottom of that fraction. And whenever you divide by 0, you get something that's undefined. So in this example, m is actually undefined. And an example of something like this, our line is to the left of the y-axis, so that would be a negative coordinate, maybe something like x equals -3, something like that. But those are the two less common examples that do come up, and a lot of times students will forget what types of equations they have. So just wanted to point that out, categorizing lines, graphs in terms of their slope. Okay, so let's pop over back to the PowerPoint. Okay, so rates of change of a line is given by the slope, as we talked about it. And again, notice since it's change in y over change in x, that is also going to tell us what the unit should be. Okay, and this is the big thing about lines. The rate of change is constant. That constant value is that slope. So other functions have rates of change that are going to differ from point to point. But that's never going to happen for a linear function. You're always going to have a constant rate of change. Okay, so let's look at this one. This is not really much of a example for anything mathematically difficult. You just plug in the numbers you give them, they give you into the slope formula. But let's think about how we would interpret the units. So we have a company selling snowboards, selling 31,300 in 2005 and 38,200 in 2011. So what are my output units? My output units are the number of snowboards sold, and my input units are years. So the slope here is telling me how much sales are increasing, only because I know this is a positive value, per year. So when we compute this, this is going to give me the average sales increase per year over that period of time. So it would be snowboards per year would be the units here. So there you go, 1,150. So over that span, sales are increasing on average by 1,150 per year. So there you go. Okay, they can also write a function using that information. The thing is, a lot of times when you have this information, you'll use something called data alignment, because a lot of times years are kind of like clunky numbers to put in. So you might say, define your variable t or x to be, let's say, in this example, what's the first data point I have? 2005. I'm selling 31,300 snowboards. So I might say, let x represent years since 2005. Really what that's doing is that's making 2005 year 0 for my formula. So if I make 2005 year 0, that would make 31,300 my y-intercept. And then my function is very easy to write. I could just say, okay, it's y equals 1,150 x plus that 31,300 number. That is my y-intercept. So let's see if they do that. Oh, okay. They say they can do it, but then they didn't actually write the line. So if you were going to do that with a previous example, that's what it would be. F of x equals 1,150x plus 31,300, where x represents the number of years since 2005. Okay. So in this one, we've got a bunch of data, and they want to explain why a linear model is appropriate. Well, we just need to determine if there is a constant rate of change here. And I'm looking at the data. I'm noticing that the y value, the water in the pool, is going up by 300 every 2 hours. So that is my slope right there, 300 divided by 2. So that is telling me my slope. It's always constant over every period of time I see in that data. That's why a linear model is appropriate. If I want to write an equation, well, again, I know my slope is 150 because it's moving up 300 gallons every 2 hours. So that's my slope, 150. How would I figure out what it was at time 0? Well, I could just move 2 hours into the past, and I could predict that basically I should have 2,500 gallons in the pool at that time. So that's what I would use for my y-intercept. So for this example, I would say f of x is 150x plus 2,500. And then for part C, we want to use that 17.5. It's an X value. We'll plug it into our formula, and that will give us the amount of water. So that's what we should be doing for part C. Okay, so they get their M of 150 for part B, which is good. V of 2 is 2800. So again, they went back and solved, and they used point slope rather than just going backwards by one step. I think it's much easier to just look at the pattern and realize it should be 2500, but they got exactly the same formula we did. The only thing to do is to plug that 17.5 in for T and solve for the volume in the pool. So that's what they go ahead and do in part C. So you get 5,125 gallons. For part D, they must ask after how long will there be 6,000 gallons? I missed that question. Oh, there it is at the top of slide 22. When will the amount of water in the pool reach 6,000 gallons? That's a Y value. So you set Y equal to 6,000 and then go ahead and solve for T. So that's what they do here. So they change the Y to 6,000 and then you solve. That's a two-step process. Subtract 2,500 on both sides. So that's why we have 150 T plus 30 equals 3,500. And then we just divide by 150. So you get 70 over 3 is your answer. So 23 1/3 hour. Okay, so this is where they move into fitting a model to data. That's a regression. We're not going to cover it in this class. They will go over it in a statistics class. I mean, I'll show you one example if you really want to see. They have all this data here. Basically, sometimes you can have data that looks linear but won't be perfectly linear, but you still may want to try and find a quote-unquote best fit line. The way to do that is to use regression. It's a technique. Let's see if I do Excel here. We'll just use the first couple of data points, and I'll show you how you can run a regression line and what that looks like. My stuff is all expired here, so hopefully. I'm just going to plug in a couple of years. And again, I'm going to use data alignment. Instead of 1980, I'm going to use year 0. So let's say year and CO2 level. So let's do the first 5 data points. So 0, 2, 4, 6, 8. Let's do the first up to 10. Okay, so 1980 to 1990 we're doing. So 338.7, 341.2, 344.4, 347.2, 351.5, 354.2. I know a lot of people in this class are business majors, so if you take the business analytics sequence, you'll be doing this in there as well. And I've created a number of videos for business analytics that you can also find on my YouTube channel where I go over this. But I just want to show you one quick example, if I remember how. Let's see, how do we do this? There's a couple of ways. I'll show you 2 quick ways. So you can insert a graph here, recommended chart. I want a line like this. So let's say this one, CO2 level, there you go. Okay, so we add this chart. You can actually do it from here, from just this chart. See, notice it's not a perfect line. It moves, it wiggles a little bit, but it's pretty close. So from here, you can do trend line. And if you click that, you'll have the option for a bunch of different modeling techniques. We're doing linear regression, so we would click linear regression. And it gives us the dotted line. I want to display the equation though too. So display the equation on the chart. So I can display the equation, and that's the approximate equation from the regression there. So that's one way to do it on Excel. So we get the rough equation. We can see the constant rate of change is about 1.5886 in the carbon level in that first year. Again, it's pretty close to what the actual data value is. So that's one way to do it. What's another way? I think probably from data. I can't remember. I'm a little rusty. Data, what if analysis? I don't think it's that, is it? That's goal seek. Data analysis. Data analysis, and then we want to do, is there regression? Regression. Okay, input the Y range, so that would be this part of the table, and the X range is this part of the table, and then we can click OK, and then we'll get a bunch of data analysis. So notice it gives us our slope value, summary output. What are we doing here? Oh, there's our slope value, our 1.588 number, and then our intercept. So there's the data that it spat out on the chart for us as well. And there's a bunch of other tools here. It's got an ANOVA analysis, and it's got the t-stat and p-values, and then some information, on the essentially 2 standard deviations away. Anyhow, that's it. That's a quick, brief summary of how to do a linear regression on Excel. 2 ways to do it. But I think we'll stop here. Let me know if you have any questions on why is it undefined for the last graph again. Oh, sorry, I'm just seeing that it's undefined. Let's have a look. Let's say we had a let's say this graph right here. Let's say we pick 2 points on this graph. Let's say, I don't know, -3, 0, and -3, 10, right? Any points with coordinates -3 are going to be on that graph. Then let's say we try and do the slope computation. All right, we do y2 minus y1, 10 minus 0, and then on the bottom we get -3 minus another -3. So that ends up with 10 over 0, which is undefined, right? Division by 0 is undefined. So that's why you're undefined when you're looking at a vertical line. Okay. Any other questions? So I will go ahead and let me see. I'll go ahead and stop here. Let me stop the recording. And